if you're here, you probably, because you hadn't taken it yet, or you're just sick about something you couldn't figure out. So there's 25 questions on the exam, all multiple choice. 12 of the questions are math-based. So 12 of them are doing calculations, so that means 13 conceptual. So pretty fair amount of both. The first thing I'm going to go over is just like some basic stuff, just to remind you. We're going to go over a couple definitions, strong bases, strong acids, and then we'll get into the good stuff. We scheduled the review for 2 hours just because these problems that we're doing take more time than the other ones. So we're just going to stay as long as it takes. So it won't be over 2 hours. If we finish early, then that's okay. So the first thing I want to go over is all the strong acids and all the strong bases, okay? If you do not have these memorized inside and out, it's time to do so, okay? So I wrote all the strong acids out over here. So there's 6 of them you need to memorize. If you don't know them, you're going to struggle on a lot of the concepts in this unit, like salts, and these pH with salts. All these things come back to whether or not you know the strong acids and strong bases. So you can save yourself a lot of points on the exam just by knowing what they are. Okay? So I wrote up what the strong acids are. Now there's a rule, a trend with the periodic table that's really easy to see what the strong bases are. So if you look in group 1, column 1 there, the alkali metals, all of those metals, if they're paired with a hydroxide ion, those are strong bases. Okay? So LiOH, NaOH, KOH, those are all strong bases. Now the second column, the alkaline earth metals, we say it's the heavy ones. So calcium and down are strong. So CaOH2, SrOH2, those are the strong ones there. Okay? So just make sure you know those strong acids and strong bases. Any questions on those?
You said that the strong bases have to be paired with an OH.
Yeah, so strong bases will always be a metal ion paired with a hydroxide ion. And OH is always a 1 minus. So if these metals like calcium always forms a 2+ ion, so to make those equal for the salt form, you have to have 2 hydroxides. So just don't forget about that. The next thing, let's go over definitions of the different acids and bases. Okay? First one, Bronsted-Lowry. Bronsted-Lowry has everything to do with proton transfers. Okay? So a Bronsted-Lowry acid is a proton donor. A Bronsted-Lowry base is a proton acceptor. It's all about transferring a proton. Okay, the next one is the Arrhenius definition. An Arrhenius acid will increase the H+ concentration. Okay? So Arrhenius acid increases the H+ concentration. These are usually in solutions. Okay? And an Arrhenius base will increase the OH- concentration. So Bronsted-Lowry, proton donor and acceptor. Arrhenius is H+ concentration and OH- concentration. And the third one is the weird one. It's Lewis. Okay? Now Lewis has everything to do with electrons. So a Lewis base is an electron pair donor. And a Lewis acid is an electron pair acceptor. So that's why oftentimes you guys have probably seen the rule that, like, if you have a transition metal ion, for example, an Fe3+ ion, why does that lower the pH? You may have saw that on the slides, that metal ions will lower the pH. The reason is because they're Lewis acids. They're deficient in electrons, that's why they have a positive charge, and they're willing to accept more electrons from those Lewis bases. So that's why they lower the pH. They're just a different type of acid. Okay? Any questions on those? Just definitions of acids and bases. Okay, good. Well, let's go ahead. The first thing that I'm going to talk about is salts. Okay? Salts is notoriously one of those things that just gives Chem 106 students a really hard time. you know, we've got this thing, what's going to do, how's it going to change the pH, but I'm going to lay out a 3-step method that if you follow these 3 steps, you should never, ever miss a salt problem, okay? It's just 3 simple steps. So, step number 1, when you encounter a salt, so here's the salt that we're going to do. Some of them are salts, some of them aren't. A salt, what is a salt? It's an ionic compound, okay? I have a cation there, and I have an anion there. There's a plus charge and a negative charge complex together, an ionic compound. So the first thing we have to do when we encounter a salt is we have to ask ourselves, step number 1, what are the ions? Okay, what are the ions? I've got this ionic compound, but if I were to dissociate that, what 2 ions are present? Okay? So, let's start with this sodium fluoride. What are the ions? Sodium and fluoride, okay? So I have an Na plus ion, and I have an F minus ion. So it's as simple as that. And one thing you need to watch out for is look out for your polyatomic ions, okay? Your sulfates, sulfides, nitrates, nitrites. Make sure you remember those. And he may not even give it to you in formula form like this. He may just write out potassium chloride or sodium sulfate. And if you don't know what the sulfate polyatomic ion is, then you really have no way to figure that out. So review those polyatomic ions that you've done before. Okay, so we've broken our salt apart. We know what ions are in there. Step number 2 is to ask ourselves, do these ions come from a strong base, I'm just writing SB, or strong acid, SA. So do these ions come from a strong base or a strong acid? Now all of the ions that you see here, they're going to be conjugates. Okay? So what I'm really asking is this the conjugate base of a strong acid, or is it the conjugate acid of a strong base? Okay? Now a rule that you need to write down is, if that ion is the conjugate of something that's strong, whether it's an acid or a base, it will not affect the pH. So conjugates of things that are strong do not affect the pH. And the reason is because they're stable on their own. They're happy where they're at. I even knew it was coming. Gosh. Jeez. That is cruel. Okay. Okay, so bringing it back to salts. Okay, so again, just to repeat myself. If these ions come from a strong base or a strong acid, they will not affect the pH. Okay? So, and the step number 3, this is the last step, is you're just going to ask yourself, will this ion act as an acid or base? Okay, so we're not talking about like the conjugate of the ion we have or the acid of the ion we have. We're talking about the ion that's in our salt. Okay, so let's go through some examples of these and we'll just go through these step by step. Step 1, 2, 3. Okay, so for sodium fluoride, we did step 1. This is going to dissociate into sodium and fluoride, okay? Sodium, does it come from a strong base or a strong acid? Yes, it's the conjugate acid of a strong base. So is it going to affect the pH? No. Let's just cross it out. It's not going to do anything, okay? Fluoride, does it come from a strong base or a strong acid? No. Good. What does it come from? Comes from a weak acid, hydrofluoric acid. So is it going to affect the pH? Yes. Okay. So I know this is going to affect the pH, and our third step is to see, well, how is it going to affect the pH? Will this ion act as an acid, or will it act as a base? You tell me, fluoride. It's going to act like a base, so it would raise the pH. Basic things will raise the pH. So I would say this would raise the pH. Yes?
So how do we know that fluorine left the base?
Because it's the conjugate base of an acid. Another way that you can tell, just kind of a trick, is that minus charges are typically bases. Things that have minus charges are typically bases, and things that have positive charges are typically acids. However, there are exceptions, so just don't go by that rule, because like bisulfate, for an example, it's HSO4 minus. It can be an acid or a base. So there are exceptions to the rule, but a general trend is that minus charges are bases and plus charges are acids. Yes?
So it's obviously not producing any more OH concentration, it's just absorbing, or it's each of those F- ions are bonding with H plus ions on the hydrogen, is that right?
So what's actually happening here is what we would do to see how this would affect the pH is we could do a problem. I have a problem with the salt, but essentially what we're doing is we're taking this F minus and we're going to run it through an ice table. So F minus plus H2O would produce hydroxide and HF. And then you can go through with your KB and whatnot and solve for what the OH would be. And
It won't necessarily interact with the hydrogen, it will mostly interact with the water.
yeah, you're just considering it with water. So with water, is it going to produce a hydroxide or is it going to produce a hydronium? Good question. Okay, let's do the next one. Rubidium chloride. Okay, Rb. So what first step? What are the ions? Rb plus and Cl minus. Rb plus, does this come from a strong base or a strong acid? Comes from a strong base, so not going to affect the pH. Just cross it out. Chloride, does this come from a strong base or a strong acid? Comes from a strong acid, not going to affect the pH. If I put this salt in water, it's not going to do anything to the pH. It's just going to stay neutral. Okay, so we'll just make a side arrow for that one, just stays neutral. Na2SO3. Okay, what are the ions? You guys felt a little less confident on this one. What are the ions? Okay, I have Na plus, but I have two of them here. Okay, so I have two Na plus and SO3 2 minus. Good. So second step. Do these come from a strong base or a strong acid? Sodium. Yes. Not going to affect the pH. Sulfite. No. Is it going to affect the pH? Yes. Okay. So this is going to affect the pH. And now we go back to this rule. Will this ion act as a base or will it act as an acid? It's going to act as a base. Okay. So this one again will raise the pH. Is there any questions on this way to do it? Yes.
So you have the SO3 and that's acting like a base. It's taking essentially hydrogen ions from the solution and that's why it raises the pH.
So what it's doing is, what I'm doing here is I'm saying if I put this in water, what's going to happen? And what would happen is this sulfite ion would pull a proton off water to produce an OH minus ion, and then the conjugate acid of this. So you're considering what is this going to do in water, and in this case, it would act like a base. Okay, let's do the next one. Ammonium iodide. What are the ions? NH4 plus, yep, this is one that you just need to memorize. NH4 plus, it's really common. It's the conjugate acid of ammonia. And I minus. Ammonium, does this come from a strong base or a strong acid? No, it's the conjugate base, or it's the conjugate acid of ammonia, which is a weak base. So this will affect the pH. I minus comes from a strong base, comes from hydriodic acid, so not going to affect the pH, okay? So now our third step is, what is this going to do? Is this going to act like an acid or is it going to act like a base? Acid. Okay, you guys are catching on. So this one would lower the pH. Okay, let's do a couple more. These next ones are a little bit trickier. Okay? Iron 3 chloride. What are the ions? Fe3 plus. How'd you know that? How'd you know it was an Fe3 plus? Because there's 3 chlorides and chloride always has a -1 charge. Okay? So I have Fe3 plus and I have 3 Cl minuses. 3 chlorides. So Fe3 plus, does this come from a strong acid or a strong base? No. What would it be? Fe2OH3 would not be a strong base, okay? Because you know it's not a strong base just by looking at it. So you know iron doesn't make a strong base. So is it going to affect the pH? Yes. Chloride, we've already done, comes from hydrochloric acid, not going to affect the pH. Okay, so what is this going to do? What's this iron going to do? Is it going to act like an acid or is it going to act like a base? Acid. It's a Lewis acid. So this one would lower the pH. Okay, how about this next one? What is it? Okay, H plus and COOH minus, we'll say. Okay? H plus, does this come from a strong acid or a strong base? Okay, it's a trick question. This is formic acid. It's just an acid. So there was a lot of people that got tripped up on the sheet today where you have a bunch of salts and then they just threw HF in there. And then you're thinking, oh, F minus, it's going to act like a base, so it's going to raise the pH. But be careful, okay? You're going to have a bunch of salts, but they can just throw an acid in there as well, or just throw a base in there as well. So don't overthink it. Just look at what it is. It's formic acid. You told me it would break up into an H+. If it's dissociating into a pure H+, it's going to be an acid. So this one would lower the pH. Okay? So don't overthink it. If it's not a salt, if it's not a really recognizable salt, then look and see whether if it's an acid or a base. CH3 minus. This is a crazy, crazy thing. It's like a, yeah. What's it going to do? What do you think? Like, what would you guess? You have no idea what this is. It would raise the pH, right? Because it has a minus charge. And you know the trend that minus charges are typically bases. This thing is like a super base. This is so unstable. This is just crazy. So this would be like one of the strongest bases ever. And it's more of an organic chemistry base, but we just want to point out that you have this knowledge that you can just look at a molecule and see whether it's going to act like a base or an acid. So this one would act like a base, so it would raise the pH. Okay, yes?
So if the ion that affects the pH is negative,
You can generally, there are exceptions, like I was saying, like bisulfate and things like that, conjugates of diprotic acids, they can have minus charges, but they can still act as acids. But yes, that's the general trend, but I don't want to say that that's the law, because there are exceptions. Okay, let's use this knowledge that you just got, and I want you to now go to this problem. What is the pH of a 0.46 molar solution of ammonium chloride? I'm going to give you guys a minute to work on it, set it up. And remember, the whole idea with these reviews is that you guys can solve these problems on your own, okay? Our job, we're going to teach, we'll be here, we can show you how to solve it. But again, to do well in the exam, you can't just memorize how to solve problems. Because as soon as he puts something in a different way, like we had on the sheet today, where you have it solving for the initial concentration, as soon as there's anything that's different, if you don't have these things mastered just inside and out, then you're going to have trouble on the exam. So you can't expect the exam to just be the same as the way you've seen every single practice problem. So make sure that you're really understanding the deep whys of these and be able to do them forwards and backwards. Oh, I'm sorry. Okay. The KB of ammonia is 1.8 times 10 to the negative 5. Thank you, sorry. Everyone's just sitting there like, what the heck? Okay, sounds like you guys are talking, so hopefully that means you're getting it with your partner. So let's do it together, okay? So this one might have thrown you off a little because normally when you do your ice tables, we're talking about weak acids and weak bases, right? You have a weak base, you react with water, you form hydroxide. You have a weak acid, react with water, you form hydronium. In this case, we did a salt, so it's a little tiny bit different. So we have to use the salt knowledge that we have to solve it, okay? So first thing, let's just go through our steps like we did before with the ammonium chloride, okay? So NH4Cl, what is that going to break up into? NH4 plus and Cl minus, okay? NH4 plus, is this the conjugate of a strong base or a strong acid? No. It's the conjugate acid of a weak base, ammonia. So it is going to affect the pH. That guy's going to affect it. Cl minus, is this going to affect the pH? No, because it's the conjugate base of a strong acid. Not going to affect the pH. So, the only reactive thing that I have in this salt is the ammonium. The chloride is not doing anything. It's only there to make the ionic compound happy so it doesn't have a formal charge. Okay? So the ammonium is what's really affecting the pH here. So what I'm going to do, if I want to see how the ammonium is going to how the pH is going to be with that in there, I'm just going to set up an ice table. So ice tables, you'll always react what you're given with water. Okay? So I'm going to do NH4 plus H2O. That's going to make H3O plus and NH3. Okay, our water doesn't matter. So what's my initial concentration of ammonium? Given in the problem, 0.46 molar. Okay? Now you guys pretty much just have this memorized right now. Since these coefficients are all 1, this one's going to be minus x because the reaction's going to be progressing that way. This is going to be 0 to start, 0 to start. I didn't have anything, I'm just pure water. And then I have plus x, x, and x. So then I have 0.46 minus x. Okay, I ran out of room, so I got to erase this. Okay, so now we need to solve for our x. So we were given the Kb of ammonia. This is one of the most common mistakes that people make, is they just take that Kb and just run with it, because that's what you were given. But in this case, we're not reacting ammonia with water, we're reacting ammonium, which is the conjugate acid. So I have to convert this into a Ka. You do that with the expression 1 times 10 to the negative 14 equals Ka times Kb. So if you take 1 times 10 to the negative 14 and divide that over, you should get your Ka is going to equal 5.56 times 10 to the negative 10. Now let's set up our expression. 5.56 times 10 to the negative 10 equals products over reactants, x squared over 0.46 minus x. Who is still confused about when you can use the assumption rule? Okay, some people. Okay, I'm gonna explain it again because I've heard people ask like, well, when can you do it? Yes.
So first of all, if you don't even want to worry about the assumption rule, can't you just always plug it in your calculator?
Yes. Yes, you can always use your solver, but some people aren't using solvers and they're doing it by hand, and so this saves a ton of time to not have to do the quadratic formula. Okay, so you can use the assumption rule when the difference between this initial concentration and your K is when the difference is greater by a factor of 1,000 or more. Okay? So if you take the bigger number and divide it by the smaller number, and you get a number that's larger than 1,000, you're good to do the assumption rule. The other easy way to look at it is 3 decimal places. So if I were to write this in scientific notation, it would be 4.6 times 10 to the negative 1. This is to the negative 10. There's 9 decimal places in between there. So I know I can easily just do the assumption rule on this one, and I can cross out this x. Do you have a question?
Yeah, it's almost always that case, right?
Yeah, it's like that a lot, but I don't want to say it's always because there's probably, to make it harder, they could make it so you couldn't. Yeah. So then you're just going to go ahead and solve for x, and when you do that, you should get x equals 1.6 times 10 to the negative 5, and x is telling us our H plus concentration, so then I can just take the negative log of that to find the pH, and when you do that, you should get pH equals 4.8. Any questions on this method? I feel like once you know how the salt works, it's just like normal. Yeah?
Can I just ask a general question?
Sure.
So, with strong acids and bases, you just negative log the concentration to actually force associate, but weak acids and bases, you always
Exactly. Yep. Okay. Any more questions on this one right here? This salts. Salt and pH. Okay, let's move on. Okay, so this next problem is a KSP problem. Okay? So I'm going to give you a minute to work on it, and then we'll do it together. If you can't solve it all the way, just at least get it set up. KSPs. It's too hot. I know, but sometimes it cuts it off. Is it okay? Now the second problem here, I'm asking the same thing. What's the molar solubility? But instead of doing it in water this time, we're doing it in a solution of barium nitrate. That's the second half of the problem.
Hey, while you guys are doing it, I'll circulate a little bit. So if you have like a question you really want to answer, please, I'll be around.
We'll do like one more minute. Yeah, same case. Same compound, same case. Yeah. Still the same. The only thing you changed is that I now have a common. basically, if you put it in water, you're not going to see what we already have. We're assuming it's just like still pure water. You're not going to have any ions. But in this case, I'm putting it in a solution which already has barium. And then we're going to see how the solubility changes if I'm just putting it in pure water or if I'm putting it in a liquid solution.
You have it in both parts, right?
Yeah. Okay, let's do it. Okay, so the theme of this unit is ice tables. So the first thing we're going to do here, we're going to set up an ice table. So first let's write out our reaction. Okay, what is the reaction here? This is a KSP problem, so we're just talking about dissociation. So what are the two ions here? Barium and sulfate, okay? So my equation is just going to look like this. Barium sulfate, this is a solid. It's going to break up into Ba2 plus SO4 2 minus. I probably wrote that one. Okay? So we have our I's. Now since this is a solid, it doesn't really matter. We're just going to neglect it here. Okay? Doesn't really matter. The change would still be like minus x here because it's a 1 coefficient. But since it's a solid, we don't put it in our KSP expression. So you can just cross it out. Okay? Now, we're in pure water. We're assuming pure distilled water. There's no ions in there. Okay? So, do I have initial concentrations of barium and sulfate? No. Okay? So this is going to be 0. This is going to be 0. And then this is going to be plus x, x, and x. This is probably the easiest KSP problem you can be given. Okay? So now I set up my expression, KSP equals x squared. So 1.1 times 10 to the negative 10 equals x squared. When you solve for x, you should get x equals 1.05 times 10 to the negative 5. Now, what's my units there? What is that x? What are the units there? Moles per liter. It's molarity, okay? What this x is, it's the molar solubility. It's the molar solubility of barium sulfate. So what's the difference between molar solubility and solubility? Exactly. Solubility is in grams per liter. So if I wanted to convert this into grams per liter, I would have to multiply by the molar mass. Okay? So there it is. Simple enough. Molar solubility at 25 degrees Celsius in water. Okay? Now how does that change when I try and dissolve that same thing in a solution of barium nitrate? Okay? So what I'm saying here is the first one, I dissolve that salt in pure water. Now I have a solution of barium nitrate, and I'm going to dissolve that same salt. What would you expect to see? Would you expect the molar solubility to be higher or lower in the other solution? Lower. It'd be lower, right? Because you see here that I already have some barium ion in there. So if you go back to Le Chatelier's principle, if I already have some ion in there, then that thing is not going to want to break up and push in that direction as much. Compared to if there was nothing in there at all, then it would just completely dissociate. If I already have some in there, it's not going to dissociate as much, so we would assume the KSP would be lower. Okay? So a lower KSP means a lower solubility. A higher KSP is a higher solubility. So let's just go ahead and set it up. Now, a lot of people asked, especially today during the exam example sheet, well, do I use barium nitrate now, or do I still use barium sulfate? Barium sulfate is our solid. That's what we're still trying to find, okay? So I have BaSO4. It's going to break into Ba2 plus and SO4 2 minus. Now the only difference here is that I have an initial concentration of barium. Compared to here I had no concentration. Here I have an initial concentration of barium. It's 0.26 molar. Everything else is just the same. This is going to be plus x. This is 0. So I have 0.26 plus x times x. So now I set this up in my KSP expression. You're going to have 1.1 times 10 to the negative 10. The KSP doesn't change. We're still talking about barium sulfate, so it's still the same KSP. Equals 0.26 plus x times x. Now this one you're going to have to do the quadratic or use your solver. But when you do it out, you should get x equals 4.23 times 10 to the negative 10. So, is this what we expected? Does this hold true to what we expected? Yes, right? When I tried dissolving that salt in a solution that already had barium in it, look at what the molar solubility did. It went over by 5 decimal places. It decreased by 5 decimal places. So, this is correct. That's one way you can check your work, is to see, is this what I would expect to see? Yes?
So the units on that would be moles of barium sulfate per liter of barium nitrate?
Yes. Yep, because that's your solution. Yes?
Solving for the molar solubility, is it always going to equal the x?
Yes, molar solubility is always the x. Okay, any other questions on this? These KSPs? Yeah? Nope, the nitrate isn't seen anywhere in our reaction, so we just completely neglect it. It's not going to do anything. Yeah? Can you repeat that?
Well, you had, for the barium, you have 0.26 plus x.
Yeah.
Why would you add that to the x for each barium? Oh, no,
Got it? Because this was barium nitrate, this was a salt, and so that would dissociate, and I would have barium ions in the solution already. Yes?
Does the assumption rule work on this as well?
It doesn't work on this one, no, because you would have to distribute these, you'd have to FOIL that out, and the only way to do it is to solve it out the long way. Yes, Jamie?
So because the x on the 0.26 is so much smaller than
Oh, I see what you're saying. I see what you're saying. Yeah, you probably could do that. I didn't do it that way when I solved it myself, but I would try it.
that's what I did it.
And you got the same answer? Okay. So yeah, so if this initial concentration is still with the assumption rule, way larger, then it's okay. But again, like someone mentioned, you can always just do it the long way, and you're going to be fine that way as well, if you get confused on when you can do it, when you can't. Okay, let's move on. Okay, so let's do this one first. This is another similar problem, and I think I needed the KSP. So would you say this is soluble or not very soluble? Not very soluble, okay, because the KSP is so small. Is it still on the board? Did it cut off? Okay, let's do it. Let's do it as a group. Okay, so the first thing you're going to do, anytime you read a chemistry problem, you want to just look at what you're given, okay? What are we given in this problem? Depending on what you're given in the problem, it can start leading you down the right path on how to solve this, okay? So the first thing I would see here is, oh my gosh, I have a KSP, okay? This is going to be a KSP problem. So what I'm probably going to have to do is set up an ice table with this salt that I have, and I'm going to see what it breaks up into, okay? I feel like I just keep moving my chalk around. So, let's set up our ice table. We have MgF2 is going to break up into Mg2 plus and 2F minus. Okay, the solid doesn't matter. The initial concentrations, I'm just in water, so I'm not going to have any. It's going to be 0 and 0. Okay, what's my change here? Plus x, yeah. What's my change here? Plus 2x, okay? This is something that can really trip you up. I have a coefficient of 2 here. That's why it's important to remember to look at this here. This is dissociating into 2 fluoride ions. So this is plus 2x. And so I have x times 2x. So what we're going to do now is set it up in the KSP expression, okay? So I'm going to have 5.2 times 10 to the negative 11 equals x times 2x squared. Now one thing to not forget algebraically here is that this squared has to distribute to both things here. So the 2 has to be squared and the x has to be squared. So I'm just going to rewrite this as 4x squared, okay? So now I have 4x squared times x. I'm going to get 5.2 times 10 to the negative 10 equals 4x cubed. Oh, sorry, negative 11. Okay, so you solve for x. X is going to tell us our molar solubility, okay? Again, the units of molar solubility is moles per 1 liter. So, reading this problem, I want to know how many grams will dissolve in 150 milliliters or 0.15 liters. So you can kind of see where this is going. I'm going to solve for the molar solubility, which is moles per 1 liter. And then I'm going to find out how many moles it is per 0.15 liters. And then I can find out how many grams it is per 0.15 liters, okay? So when you solve for x, you should get x equals 2.35 times 10 to the negative 11. Did I mess that up? Oh, negative 4. Sorry, I can't read my handwriting. Moles per liter. Okay? So this is moles per liter. So, I don't have 1 liter here. I have 0.15 liters. So I have to multiply this by 0.15 liters. Liters are going to cancel, and that's just going to leave me with moles. Okay? And then once I have moles, then I can find out how many grams are there. Okay? So after you do that, you should get 3.53 times 10 to the negative 3 moles. And then going from moles to grams, there's 62.3 grams per 1 mole for MgF2. So your final answer should be 2.2 times 10 to the negative 3 grams. Okay, this is probably one of the harder KSP problems that you've seen so far. Okay, but it just brings back some of those things you learned in Chem 105 and just working through these units. Yes. Hey, do you guys mind quieting down a little so I can hear you? Yeah.
With the diatomic molecule, chloride should be associated with two of these atoms.
How did I know that?
Because I was taught in 105 that those molecules almost like naturally stick together the same diatomic.
The reason is because it's not diatomic here. Because this is an ionic compound, they're in ion form. So the reason that you know, well, there's a 2 right here, so you know there's going to be 2 of them, and fluorides always form a 1- charge. And then if you look at the periodic table, you'd also see magnesium always forms a 2+ charge. So that's why I need 2 of those fluoride ions. So yeah, we're not talking about like the fluorine gas here, F2. We're talking about ions because it's an ionic compound. Yeah. Say that again. Yeah. Yep. Okay. Any other questions on this? So this was a hard problem, but you guys have enough to figure it out. Okay. So hopefully this maybe sparked some interest, and you can start make some of your own problems. You know, give yourself a volume and make one of these out and solve what the molar solubility is. Okay. Let's do our last problem. And then I'll give it to Braden. He's going to do titrations. Okay, so you mix 2.3 times 10 to the negative 4 molar solution of C8+ with 20 milliliters of an 8.8 molar solution of carbonate. Calcium carbonate, KSP is this. Will a precipitate form? Okay, this is some... Should I just give him a minute? Okay, I'll give you a minute just to set it up or so. This is a tough one. This right here? Yeah. Yeah, that's a 4.
it's just exercise, not like initial salt reactor, initial salt, like all of this never matters, right? Never matters how much you add. It's always going to look the same, unless something like this, the solution already had one of these here. And then there's something here, like we did on that other problem. So for this problem, ASP is equal to x to the 1 how much of each one of those two components is in here?
Yeah.
Towards the solid. And then you just draw the arrow. And so if Q is bigger than K, it goes this way. So it goes down towards the solid. Okay, with that
Okay. All right, let's do it. So, this was a problem. It's similar to one on his slides, okay? So if you guys go on lecture materials on Learning Suite, and then you go to the last lecture from material, it was last Friday, he has all these good problems, these KSP problems in the PowerPoint, and then if you look, he's posted a PDF of all the solutions. So there's really, really good problems on there. You need to go through and do all of them and follow his work and find out how to do each and every one of those. This one's really similar to one of the ones he had on there, okay? So the first thing, I'm reading the problem, I see KSP. Great, okay? I'm going to set up my KSP expression. So I have KSP is going to equal, in this case, it's the concentration of calcium times the concentration of carbonate. Now, just to explain what's happening here is I have two beakers, right? One of calcium ions, one of carbonate ions, and I add them together. And I want to know if a precipitate forms. So what I have to do is I have to find out what these concentrations are, okay? And then, depending on what this comes out to, we can see if it's going to precipitate or not. I'll show you how to do that, okay? So first thing, I have 10 milliliters of 2.3 times 10 to the negative 4 molar of calcium. So the first thing I have to do is find out how many moles is that. So, if you just use the molarity equation, molarity equals moles per liter, my molarity is 2.3 times 10 to the negative 4 equals moles over liters. My liters is 0.01. When you solve for that, you should get 2.3 times 10 to the negative 6 moles of Ca2+. Now again, for my KSP expression, I need a concentration of Ca2+. So what I have to do now is I have to divide by the total volume that's there. Okay? So my total volume here would be 10 milliliters plus 20 milliliters, total of 30 milliliters. So I would divide this amount of moles by 0.03. And that's going to give me my concentration of Ca2+. And when you do that, you should get, where am I at? 7.67 times 10 to the negative 5. Okay, so we have Ca2+. We're going to do the same thing for carbonate now. Find out how many moles that is. So the concentration of it times the volume in liters is going to give me the moles. And when you do that, you should get, let's see, this one. So 1.53 times 10 to the negative 6 moles. And again, I need a concentration, so I'm going to divide by the total volume. Divide by 0.03, and that should give you 5.87 times 10 to the negative 2 molar. So now I have concentrations for calcium and for carbonate. So what I'm going to do is I'm going to plug those values into here in my expression. So I'm just multiplying this by this, okay? Now, how you solve this problem is if you go back and you remember your K's and Q's. Okay? So if K is greater than Q, here meaning the KSP, then my reaction is going to go to the right, away from the solid in the reaction, towards the ions. So this would be no precipitate. If my K equals my Q, then what? My solution is completely saturated. If I added one more drop of calcium, it would precipitate. So we'd say this is a completely saturated solution. Okay? And if my K is less than my Q, then it's going to go towards the left, which is towards the solid in our reaction. So this would be a precipitate forms. So in this case, what you're going to do is you're going to multiply this by this, and this is going to be equal to the Q. Okay, because it's not the KSP. I told you what the KSP was, and in this case I'm solving for what the Q is with those concentrations. And when you do that, you should get 4.5 times 10 to the negative 9, was it? Oh, 4.5 times 10 to the negative 6. Okay? So my Q is greater than my K, so a precipitate would form there. Okay, if this, I know, I'm sorry I had to go a little fast. Braden's ready to do titrations. He just can't wait. He's just standing up here.
Can't
He's
wait.
so anxious.
We decided on an hour.
So if this was a little fast and a little hard, go back and watch the video again and go back and do the examples on his slides because they're basically the same exact thing and follow his work on there. Okay? Any questions on that? Okay.